Hello, welcome to another video of our series about 3D tools in automotive design. This time, an expert shows you how to work with Luxoft Populus. The task: create a working mock-up demo of an instrument cluster in under 15 minutes. Okay. Challenge accepted. Let's start. First, we create a new project. Let's call it Mini Cluster. Leave this option checked to let Populus create some sample contents and click Finish. Our project has been created. You can find it in the Project Explorer window on the left. The DDH folder contains the file with the HMI database. A default page is already available. Serialize the project and run it. Our first Hello World page. Now, let's delete the default Hello World text, because we will add our own graphical assets in the next step. Go to the master settings and change the display size to match our demo size. For our demo, we also need a functional unit. Functional units are interfaces that abstract data from the actual physical sources and provide unified access. We can also use functional units for simulation and testing. Let's call our functional unit board computer and set its ID to 10. Now we have to define which kind of data our board computer should provide. Create two types of dynamic data. The current vehicle speed. It's of type speed. And the fuel level. We can use an integer for that. Those are the variables for the instrument cluster. We also need some indications, also known as telltales, to show function states, warnings, and errors. Our demo has 5 custom indications for handbrake, battery, oil, ABS, and high beam on. Save the changes. Now it's time to import our bitmap assets for background and graphical elements. It's good practice to store them in a new dedicated bitmaps folder. You can just drag and drop all your assets. Go to the Bitmaps tab to define names for the bitmaps. Add all the bitmaps you've just imported to the list. These names are used as internal handles to connect logic and bitmaps. They are already set to be used on the default page. Next, define which bitmap should be used as the background. Go to Properties and select the correct bitmap name for the background bitmap field. A preview shows up. Now it's time to create a panel for the telltales. Name it Telltales. Set the position for the panel. You can define the exact size and position in the Properties tab. Then, set the background bitmap. This is the one depicting all the telltales off. Now, each telltale gets its own static bitmap field. starting with the one for the handbrake. position it over the background image. And add the bitmap for the visible state. Do the same for the other 4 telltales. Note that neat trick. You can mark more than one element here and edit them in a table-like edit mode. Adapt names and positions. Finally, set the correct bitmaps for the visible states. The telltales shouldn't always be visible. Their visibility depends on the data from our functional unit. We have to add an expression for the indication to deduct the visibility. They all depend on the data from the board computer. Connect each indication's expression to the corresponding board computer data. Okay, that's done. Now it's time to add yet another panel. This time the one for the gauges. We have to define the scale and the needle behavior. For the scale, we define a graphical scale field. And name it speed. Place it in front of the speedometer scale background. And connect the scale data to the speed delivered from our functional unit. The scale has a certain range. So, don't forget to set the angles for the minimum and maximum values of the scale. Next, set the appearance type to gauge, because our speedometer shall behave like a classical gauge. You can even set an animation filter to simulate physical behavior. We use a PI deregulator to mimic the transient response of a real needle. Finally, we add the bitmap for the needle. And center it. Don't forget to set the start and end angle of the scale so that the needle does not exceed the scale. The last cluster element we have to implement is the fuel gauge. Again, we use a graphical scale field for that. This time we name it Fuel. Set the correct size and position. And connect the scale data to the fuel data from the board computer. As before, the scale needs a minimum and maximum scale value. The appearance type is gauge again. And we also have a start and end angle. But this time we don't use a needle. Instead, we use a fill bitmap to show the fuel level. All the elements are now added and configured. Time to serialize the project. With everything successfully done, we can run our demo the first time. Mission accomplished. Our demo cluster is up and running. Now, let's do some tests. Go back to the Project Explorer and create a DDH runtime. This is a graphical user interface where we can see and change data for the functional units. After creation, set it as the active runtime in the Project Explorer. In the Runtime tab, select the board computer from the list of functional units. Here, you can find all the indications and dynamic data we defined earlier. Now we connect the functional unit simulator to the Populus engine of our demo cluster. You can connect to Populus engines on real hardware in the same way. Just use the hardware's IP address instead of the local host. Okay, demo and runtime are up and running. Let's change some data. Activating Telltales works fine. Speed and fuel values are also represented correctly. Smoke test passed. Wow! We've just created an instrument cluster mockup from scratch in 12 minutes. We've even had time to do some basic tests. Impressive, innit? But Populus has much more to offer. You can now add more cluster elements, create localized versions, and even add skins to have different graphic designs, such as day and night mode. Visit Luxoft.com and check out all the functionality Luxoft Populus has to offer. Thanks for watching.